simplest form, just two variables, to a basic identity that you are doubtless already familiar with, referred to as Bayes' law. The basic idea being we have a joint probability. That's a symmetric expression. H and O play an equal or equivalent role in that expression. So we can expand it in either direction, right? So we can write P of H given O times P of O, or we could equivalently write P of O given H times P of H. And we just move the term over to the other side, and we can now express the conditional probability of H given O in terms of probability of O given H, the exact converse, times the unconditional probability of H, divided by probability of O in the denominator, which, as you'll see in a moment, is typically written in Bayes' law applications in this expanded form, where we expand probability of O basically just as a normalization. In other words, it looks exactly the same as the numerator. It's just summed over all possible values of H. Now, the letter choices of the variables here are not an accident. By H here, I'm referring to a hidden variable, and O, I'm referring to an observable variable. So this now becomes the direction that we typically want to predict. In other words, we want estimates of the probability of some hidden variable given what we've actually observed. And we compute that in terms of the exact converse, that is to say, what you might call a model of what we would expect to observe if we just assumed a particular hidden state. Okay? So the whole point of the beauty of models is models are self-defining. I make up a model. I say, oh, I think this process is binomial. Oh, okay. I can immediately write down a likelihood for that, right? Because when the instant you say binomial, you're saying, I mean the following model that says the probability of observing 5 rolls of the dice out of 12 to come out, say, 6s, under just considering that to be a multinomial process, I can immediately get an expression for this. And then I can use different models, likelihoods, basically to see which model best fits the observations. And then Bayes' law, we get posterior probability estimate for which of our hidden models seems to have highest probability, for example. Okay, so this is a basic foundation for statistical inference that we're going to be using over and over and over again.